title is self-explanatory. How can we use information about the morphology of Spanish to have a better tokenization and hopefully also better language modeling? So, this should be obvious that tokenization is a crucial part of neural language models, but it really isn't, because if you look at the major conferences, the amount of publications on this topic is very, very small, and many people consider tokenization as a solved problem. But I'm going to argue that it really isn't that. Why is that? Well, it shapes the vocabulary, because what gets into as input to the model is determined by what kind of words you have in the vocabulary. So depending on how you split the words, how you represent them, you will have different kind of input information inside the model. So it will affect the size, the efficiency, and also the coverage, what kind of words are represented inside the model. And then very importantly, it influences how morphology and the meaning are connected, right? Because as we know, in a model like transformer, every token is represented as a vector, and this vector is supposed to represent meaning, right? But how can it do it if a word is split into 5 items, right? So that's why the representation, the connection between the meaning and the form is sort of proxied by morphology and by tokenization. Okay, and then of course, at the end of the day, it does influence the performance on downstream tasks. So how it was done in the future, this is a reminder from the basics of NLP. So the early models for distributional semantics were using full words as tokens, right? So every word with some very easy and dirty rules for removing punctuation and spaces can be used as a separate word. Now, there's a problem with that. Well, many problems. Your vocabulary grows, right? So you have, I don't know, 100,000 words in a modern language. So if you take into account the syntactic changes the words undergo, you are quickly into millions and millions of words. So you can't represent that. So in a way, you have too many words, but also you have too few, right? Because on the other hand, there can be new words that you don't have in your vocabulary, but you want to have a reasonable representation for them as well, right? So this is not a very good approach. So what currently is used is subword tokenizers. So these are all of these, and they have a very simple rule. What they try to do is to represent common and normal words as individual tokens, but if a word is not common enough to have its own token, it's going to be split into sub-elements that hopefully can carry some meaning on their own, right? So BPE is the baseline I'm going to deal with. So who knows BPE here? Okay, minority, which is great because I have some content prepared. So BPE is called byte per encoding, and it's a type of representation that is trained. So it's not like any a priori thing, but it's going to be trained to efficiently represent words on a specific corpus. So what it does is you give it a very large corpus that is somehow representative for the language you're going to model or set of languages. And then you convert the input text to a sequence of bytes and initiate the vocabulary with these bytes, right? So every possible byte is represented as a vocabulary item. And then you go through the following loop. So you find the most frequent pair of subsequent tokens that are just occurring one after another. So at the beginning, they would be bytes. And then you create a new token that is just the concatenation of these two. And then all of the occurrences of these pairs of tokens are replaced with this special token, right? And then you repeat it until you reach a desired size. So desired size can be between 40,000 and probably 100,000 for typical vocabularies, right? And yeah, so it's very simple. But what will happen if you go through this process is that the words that are common will have their own individual tokens because they will occur frequently enough to go through that loop. The things that are less common are going to be split. And in the worst case scenario, we can represent anything in the worst case scenario using a sequence of bytes, right? Unfortunately, very often the worst case scenario is the actual scenario we are dealing. Okay, so these are a few examples. This is for English, just because it's for English speaking audience. So these are a few words that are kind of compound, right? So you can see that you would like to have some kind of phenomenon of compositionality happening within them, right? Because super bizarre is connected semantically to the word bizarre, and then super is like a prefix. that adds extra element of meaning, right? Electroneutral, undeniability, all of these are compound words. So we would like them to be split like this, right? If they have to be split, of course, they can be represented as individual tokens, but these are not very frequent words, so they would probably be split into smaller ones. So I don't know, undeniability is the negative prefix, the stem, which is from denying, right? Able because it's from the ability, and then ity being a suffix for a noun coming from an adjective, right? Okay. Unfortunately, they are split like that. And this is on the default BPE, which is specifically trained on English data, right? So if you test it on other languages, it will be even worse. And I mean, it's not what we want, but it's even worse because it's kind of using words that are not part of the semantic field of these, right? So super bizarre takes superb and then adds this bizarre, which is nothing. But what's worse, it's going to have the semantic representation of superb inside the representation of super bizarre. So we definitely don't want that. Electron neutral is probably better because you have the electron here, which is somehow connected, but then you have EU here in the middle for some reason. And yeah, bidirectional, right? You would like to have the bi, right, indicating two directions. Instead, you have bid, which is again completely different. Right? So you can see it doesn't work. This is the final motivational example specifically for this audience. If you have a Polish word, then you would like probably something like that. Instead, you get this. And then the problem is even worse in languages that are further from English in terms of their alphabet, right? So what you will get if you use Arabic is you will get many tokens that are not even printable, right? Because the Arabic UTF multi-byte code points are split into without respecting the boundaries between the characters. Okay, so this is of course not ideal. Yes, of course.
If you have like a morphologically simple word so that you cannot split, but
yes,
it's very, very low frequency.
Yes.
What does it happen?
What has happened in practice or what we would want to happen?
I mean,
so what happens is it's going to be split on like even shorter elements. So you'll get a one letter token or 2 letter tokens. Okay. So this is, of course, the problem, right? The statistical tokenization, even if it's trained specifically on the language that we want to represent, it's just ignoring the morphology. And then you get splitting across meaningful morphemes. So what will happen in practice? Well, it will not generalize very well to answer forms, right? Because especially if we're talking about syntax, there will be many, many forms. And then, you know, the meaning of the word in one form should be probably connected to the meaning of the same word in another form, right? So it will not have that because it just doesn't generalize. And then there will be the problem of semantics, which I already mentioned. And then the final one, well, almost final one, is reduced interpretability, right? What happens if you imagine you have your interpretability tool, and then it kind of highlights the elements of the sentence that your model was using very heavily while making these decisions, right? If these elements of the sentence are, you know, is, then you know it's worthless, right? And then the final, there's like an economic impact of this. Can anyone see what's the economic impact?
The number of tokens.
Exactly.
Generate the answer.
Exactly. 10 points for the gentleman. So if you're adding the same, asking the same question to ChatGPT in Polish and in English, and your question is going to be, and the answer is going to be split into 3 times more tokens, you're going to pay 3 times more for the same thing, right? So probably we don't want that if we are speaking one of the smaller languages. Okay. So why are we dealing with Spanish? Well, I would wish this project to happen in Polish, but unfortunately the student is Spanish. However, in defense of Spanish, it does have some morphology richness, right? So it doesn't have the nominal inflection, so the nouns are what they are. However, it does have quite a bit of diversity in terms of verb forms, right? So this is the verb hablar, which means to talk, and it has a gerund form, and then it has the past participle, but then it has all of these forms for 3 different past tenses, and then present, and then conditional, and then future. And then you can see that unlike in many nominal inflection patterns, there isn't much repetition. There's just 2 words here that are repeated. Everything else is completely unique, right? So we can see when we have a verb that's like that, I mean, it would make no sense to represent them separately, but on the other hand, we don't want to lose connection between verbs, right? So we want the representation for hablabais to be connected to the representation of hablas, for example. And then there's also subjunctive and all of that. Okay, so people, of course, looked at the problem in the past, and what they found is kind of mixed. So there are specific languages that people try to approach. So Turkish is the famous example because Turkish is a very agglutinative language. So it has these giant words that connect many aspects of it. And sometimes people have seen improvement, but sometimes not. And these negative examples are kind of difficult to interpret because they focus on very narrow phenomena. So sometimes people check like whether I don't know, the genitive is represented properly in the tokens, right? But we care more than about just one single phenomenon. And then people sometimes compare different languages. So they would compare a sentence in English and the sentence in Turkish and checking how it's represented. However, no one has done a study like this one, like just taking a single language and then comparing two different tokenizations. And that's what we're going to do. Okay, so this is the question. Can we build a better tokenization and then whether it will improve large language model performance, right? So, I mean, the motivation is clear, but whether it will improve performance is not clear, right? Because we are representing the tokens in some ways, but then the transformer has all the layers above. So it can learn connections between words, even if they are not represented ideally, right? So let's see. Everything clear so far? Okay, perfect. So we focus on Spanish. And Spanish is a big language, but it's actually not that well explored. So if you look at the amount of studies, there's English, there's Chinese, and then there are other languages. So proportionally to the use, which Spanish is a very widely used language, it's actually not that well explored language. So we're going to focus on that one. And then we're going to build a morphology-aware tokenizer. I will explain what happens about it later. And then we will take the tokenizer and use it to pre-train a large language model from scratch and then perform evaluation. Evaluation both in terms of how good the language model is at language modeling, but also how good the language model is in downstream tasks. Okay, let's go. So this is the most boring slide, but it's also very, very important one. So what would be tempting to do is just build a morphological analyzer, use it to tokenize the tokens, to the words into tokens, and then feed these tokens as the representation for the language model. Unfortunately, that is very complicated, requires additional code, and does not perform very well and doesn't generalize very well. So instead of that, what we did is we trained a segmentation model, and then we selected the best one, and then we take a big corpus, we segment this using our morphology-aware tokenizer, and then we take this data and give it to BPE as training data. So if you look at how training in BPE happens, you can give it a special token saying always split on this special token, right? So we pre-tokenize the data, we train a BPE, and then everything that happens from then on is completely normal. You can take this BPE, you can use 100% native Hugging Face code just with a different vocabulary, right? Is that clear? So that it very, very much simplifies the data. The setup, I mean, we lose some performance because there might be cases when BPE learns a different thing that we would want. So anyone, you can ask questions later. I can show you examples how it can go wrong. So then we get a balance because we have the linguistic informativeness, let's say, but at the same time, it also remains statistically efficient and usable because it's using the BPE in itself. Because, I don't know, if you take this vanilla one, what will happen is it will have no idea what to do with English, right? And there will be a lot of English text in whatever corpus we have. So you want it to be, to have a BPE as a fallback also, right? Okay, so how that works? So first of all, we need the tokenizer. Well, the morphological splitter. And unfortunately, there isn't very good gold standard data for Spanish. Also, morphology is difficult, surprisingly so, for me at least. I think there is no clear way to split the word. And because of that, the resources are not very strong. So what we are using is called morphogram. Has anyone heard of morphogram? No. So this is a funny thing because this is an unsupervised segmenter. Unsupervised in the sense that it has this kind of grammar which is telling it that this is the structure of a word, right? That the word has a stem, has a prefix, has a suffix, and then it has morphs, and then these morphs have submorphs. And then what it tries to do, it's kind of complicated, but it's a probabilistic grammar. It tries to find a representation for these words that best fits this model. Right? So it's kind of doing a similar thing as the BPE does, but instead of being like anything can be connected with anything, it says actually this kind of structure has to be followed. Right? And the way it works is you give it an input lexicon, which is, we gave it 50,000, the most common words in Spanish, and then it tries to fit these two things, which is never going to be perfect, but it's better than nothing since we don't have training data for morphology splitter. And also the nice thing about the setup is that you can extend it by adding things that you do know, right? So for example, you can provide a list of these prefixes and suffixes that are known, and it will try to include them as well, right? So it's a semi-supervised model essentially. Okay, so what we did, we just trained it in the unsupervised method way and also in semi-supervised way. And also we compared to like an older model. And these are the examples. It's kind of hard to interpret them. So what you want is you want the reference splitting to be followed in the same borders, but also we have the stem. So it would also be nice if the stem was recognized. So this one is, for example, you configure it, and then you can see this is the reference. And actually morphogram unsupervised does a better job than the semi-supervised, which kind of puts everything in a single token. But the stem is not, the problem with this one, the unsupervised one, is because it doesn't know the prefixes and suffixes, it likes to put the stem as the last element, which is not what we want. The semi-supervised is better at recognizing it, but still the international, which is international, you would like the nation to be here in the middle, nation, right? But this one takes an intern, this one has an N. So just looking manually at these results, it's kind of hard to see which one is better. So that's why we have proper evaluation. So the evaluation works like that. There is a predicted splitting and there is a gold standard splitting. And then we do two things. The first one is boundary precision and recall. So you treat the boundary markers as tokens, as things that have to be recognized, and you compute the precision and recall over those. Right, but for this, you need gold reference, right? So unfortunately, the time has come and someone had to sit down and annotate a big number of words in Spanish. So we took 1,200 unseen words. By unseen, I mean not part of this lexicon. Even though the lexicon is used in a unsupervised manner, it's still cleaner and nicer to use completely new words. So this is 1,200 most common words that were not in the dictionary for unsupervised training. And then 5,400 words from text. So here, these are individual words in the sense of lexems, right? And this is just a short corpus that is annotated. So there will be a lot of repetitions. Also, this corpus is much easier, right? Because you will have a lot of simple words that never are tokenized. Okay, so that's what happens. So this is the old school model, the one that's not doing too great. And this is morphogram, and it's performing much better in the semi-supervised way, and that the results are around 70-something, 80-something. So the results are not perfect. Unfortunately, because well, it had no training. But for a model that's unsupervised or just semi-supervised, it's actually quite a good result, right? 77, 88. Oh, the other measure is not looking at the boundaries, but it's looking at morphs. So these are the morphs, and then it's looking whether the morph from the input is represented in there, right? Okay, so based on that, we just select the semi-supervised morphogram for the next stage. Okay, and that's what we do. So we take 10% of the Spanish Oscar, which is a, you know, Oscar, right? It's just a big corpus scraped from the web of not great quality. And then we have these words. This is an example. And then what we do is we insert these special tokens between the recognized morphs of the word. So I don't know, posibilidad is split into pos and ibilidad, and we put this token, and then we instruct BPE, do not split, do not connect these tokens, right? So yeah, and then we train BPE, and we'll see what happens, right? So to summarize, in the second stage we will be training 2 BPE tokenizers. So we have our Oscar, we split it. Segment it into using morphogram, and then we train a morphology-aware BPE, but also we train vanilla BPE with exactly the same data to see what happens. I mean, this model is still going to be better than the BPE you have in BERT, right? Because it's been trained on Spanish data rather than random collection of data with mostly English. Okay, and again, some examples. So BPE has this, adds this space as part of the token. And this is an example, and you can see that some things work better. So for example, dormía, which means slept. So this is split into the stem that is sleeping, and then ia, which is the ending for the past tense. Some things are split even though they shouldn't be. Viento, which is the wind, is split into viento, which makes no sense whatsoever. So again, individual examples, hard to assess. So we need to evaluate. So for this one, we have the same evaluation. So what will happen is we can measure these, and then what else we can compute is the subword fertility, because there will be a cost for doing all of that, right? Because inevitably, if you split words according to the morphology boundaries, you will get more subwords than you get initially, right? Because you will separate, if you have a very common word and it's a verb, probably it will be represented as a single token in BPE. But if you ask the BPE to respect morphological boundaries, it will split it into 2, right? So we don't want too much of it, but it's inevitable that you will get more. So if we compare the morphology-aware tokenizer with the standard tokenizer, the fertility jumps from 1.12 to 1.45. So it's not too much, but unfortunately there is a price to pay. Okay. Okay, and yeah, anything jumps about these results? 0.67. Well, it's lower than what I just showed you as the performance of our tokenizer, right? I just said that the performance of the segmentation model is 77, and now it's 67.
Well, see why you are combining like BPE and
exactly. Another 10 points for the same person. You have to improve your game. Yes, exactly. So if we do that, if we go through that process, we split the text and then we give it to BPE. The BPE will learn some things, but it's still BPE, right? It will still make some decisions. So, for example, maybe which was the example I was showing. That was that was the example of, well, anyway, the example doesn't matter. What will happen is sometimes it will learn, for example, that some things numerosos have to be split, but maybe there's another combination when the token will appear, and then BPE will just do its own thing. So we can't control it perfectly, and this is the price we pay for using BPE instead of using our tokenizer directly. That the performance of following the tokenization that we want is dropping a bit. However, it's still quite good. So this is another illustration of this time in terms of morphs. So you can see here for gold standard, these are all the morphs in the text that were split manually according to their length. So 1, 2, 3, 4, 5 characters. And then on the left and right, you have the morphs from the morphology-aware tokenizer and the BPE tokenizer. And these colorful bands indicate how many of them were shared, right? So you can see that the further you go, the less of them are shared. But generally, there is quite a strong one-to-one connection between the gold standard tokenization and our morphology tokenization. For 5+, it's probably the weakest because the longest words are the most difficult. However, for BPE, I mean, from the morphs that are 5 characters or longer, only, I don't know how much is that, 10% are actually true ones. Everything else is fake, right? And the purple line says how many morphs were true for BPE, but were not true for morphology tokenizer, right? So these are real failures that the automatic statistical method works better than what we did. And this is like a very thin line here. Right? So there's very few of them, and mostly in these 5+ category. Okay, so it works. So that would actually help with language modeling. So here we have our BP, our morphology aware BP, and this is actually the work I was involved in directly. So here we train Roberta. Unfortunately, the problem with tokenization is that because it lies at the very foundation of the modeling, you can't really fine-tune the model or trim it or whatever. You have to train it from scratch, right? So this took hours and hours of compute. We also used FineWeb, which is a much better data set for training language models because it's clean, it's much nicer than OSCAR. And then there's the problem of masking, right? So let's jump straight into that. So I'm sure you remember that BERT is trained on masked words prediction. However, the problem is if you start splitting words more finely, what will happen is the task becomes trivial. So if you say im, pre, this is the masked token, and then ible, then anyone who's a Spanish speaker will guess the word immediately, right? Without any knowledge about the semantics of the fragment or whatever, right? So the task becomes a bit too easy if you only mask a single token, right? That's why we experimented with masking a bit. So the other things that people did in the past was extending the masking to the end of the word, right? So you also mask this part, or just mask the whole words, which also affects the percentage of the masked tokens, right? And depending on how you did that, you get different models. And you don't, well, I'll show you the results. I'll let them speak for themselves. Okay, so we have a small data set, and then we have these masking strategies. And then what we do is we train our standard BPE with 3 different masking strategies and our morphology-aware tokenizer with 2 different masking strategies. We skip the naive one because it's quite obvious it's not going to work well. And then when you compute the perplexity, you also have to do masking. So again, here also you can use different strategies, right? So we have all these combinations, and then we just compute the perplexity, right? So we do that and in using a perplexity and then also bits per byte. Can you see why perplexity is not a fair measure here? This is what the reviewer said.
I think it's computed, it should be normalized for the number of tokens, right?
Yeah, exactly. Again, 10 points. So the problem is that perplexity is just measuring how difficult it is to guess the word, but it depends on the vocabulary, right? So if you have a model that has smaller and easier words, it becomes much easier to guess the token, right? Whereas if you have a tokenizer that has 500,000 tokens, it's a very difficult task. That's why, apart from perplexity, we can also use bits per byte, which is normalizing for the length, for the size of the vocabulary, or conversely for the length of the token that you're trying to predict, right? However, this is just for the general interest because it doesn't really change the results. The results are that from the standard VPE, actually the naive one works well best, which makes sense because most words are not split, so probably the naive masking is enough. However, for the morphology aware one, we get the better results for left to right, unless the perplexity is also measured on whole word, right? So we get a bit of a home bias here, right? Because it's best to train a model on the same setup that the model will be evaluated. But based on that, we just use the vanilla language model as a standard BP tokenizer, and then morphology aware one with left right. Okay. However, these results already show that we're better, right? Because this is perplexity, lower is better, and we're actually quite lower than BP. And then the further experiments, we used Lambda, which is similar to perplexity because you measure the probability of a word. You ask the model to guess the word. However, here the words are are set in a specific way, which means you have to understand the whole fragment to guess which word goes here, right? These are not individual words. So these are the final words. And for the sake of completeness, we also used random words, which makes it work a bit more like perplexity. And then we just check whether the model guesses that right? And then we compare the probabilities, right? So we compare the probability of the last word being Sibyl from our model and from the reference model, right? Now there's a complication. I'm not going to guess you what it is because the complication is it's hard to it's not trivial to represent the probability of a word when the word is split into multiple tokens, right? Because the probability is always conditional on the everything else, right? So because of that, we had to go through this a bit of complication by using a joint probability, right? So if you have the word centilla, we first compute the probability of cent given the context that is before, and then we add ia as a probability, right? This sounds complicated, but actually it doesn't change that much because the probability, the first one actually matters. Once you fill in the first token in a sequence, then it becomes quite trivial for the model to guess what follows. So this probability is 0.99. So it doesn't change much in practice, but it has to be done for comparison. Okay. And the other type of test we did was agreement test. So here we are testing the specific syntactic abilities of the model, which is an example like that. The cat who ate the mice either sleep or sleeps, right? So that you can see that the example is tricky. It should be sleeps, right? Because the cat sleeps. However, you can see that the mice are just before, right? Which is a noun in a plural form, right? So it's tempting for the model to just agree with the word that it has its closest, right? So they are specifically designed to be tricky in that way or adversarial. And yeah, and then we check whether the model guesses the right word here. Okay, and these are the results. So yeah, for this, it's actually worked great, right? So for the final word prediction, we get a jump from 33 to 0.400. So it's still difficult, right? It's still difficult, but we get a much better result. And then for the random one, better results, of course, because these random words are easier to predict, but still a very big advantage. And then in the morphosyntactic test is just wonderful because we cut the error in half, right? Which is a very nice thing compared to a model that's just trained with state-of-the-art for a given size, right? So it can improve the syntactic ability quite substantially. Okay, so this is just syntactic tests, and then the test for language modeling, which is the valid task, but we want to know whether it actually influences the downstream tasks. So in downstream tasks, the model has the ability to learn something about the task that's maybe not directly related to the syntax understanding. So we don't expect such a large gains. At the beginning, we didn't know whether we would get any gains at all. And we have like 3 tasks that were just easiest to find resources for Spanish, because again, this is all for Spanish, so we don't have glue and everything else. So we had natural language inference, we had the paraphrase identification, and then semantic text similarity. And all of them are somewhat related to syntax of the sentence, but not directly. Anyone wants to guess which one of these will give us highest gains thanks to better syntax understanding? Anyone?
Yes.
Which one?
Paraphrase.
Okay, let's see. The first one. You're saying the
No.
first.
No, I said paraphrase.
Paraphrase. Okay, let's see. Okay, let's see. And yeah, we just train them. We do a small hyperparameter search, and the results are bigger on STS. 10 points, which is not something I expected, to be honest, because text similarity is somewhat vague, and the similarity between these examples are sometimes is kind of thematic. But of course, I was wrong, and really understanding of the syntax of the sentence really helps in STS task. Well, really, we get a few percentage points, and then for the other ones, we get quite small increments. They are still increments and they are consistent across all the experiments we did, but they are small gains. Okay, so that's it. I think I'm good for, well, it's taken a while, but conclusions. So what we've learned is that I didn't talk about that, so that the morphological segmentation does benefit from linguistic knowledge, right? Because at the very beginning, I showed that adding these prefixes to the model helps it. So the semi-supervised model is better at segmentation than the completely unsupervised one. And then the morph-aware tokenizer based of that has a stronger alignment with gold segmentations, even though it's limited by the fact it goes through the BPE stage, right? And then it has slightly higher subword fertility, so you pay the smaller price, but the tokens are definitely more linguistically meaningful. And then the model gets very large gains in the morphologically sensitive tasks, and then smaller gains in the general tasks, but still noticeable improvements. So this is the key takeaway, that the morphology-aware tokenization improves Spanish language model quality. Yeah, the thing that's nice to emphasize is it's a very simple approach, but it's quite effective. So to achieve all that, you didn't need to actually modify anything about the tokenization algorithm, nothing about the model architecture. You just plug in a different dictionary. So thank you. So the only thing we needed to do is to change the vocabulary for the model, and everything else works. So and then if you want to do it for your own language, which I thoroughly invite you to do, what you would need to do is use the morphological segmenter. So these rules that I showed at the beginning of the prefix and suffix, but this one probably works for any European language except for Turkish. So we can just use that. And then you would need to do evaluation. So a small portion of the language manually segmented is necessary to choose the best configuration, right? And then, and then if you want to work in Spanish, which would be great as well, we are releasing all the segmentation models and the reference data, all these manually segmented words, the lexicon, and these affix lists which were necessary, as well as models and everything else. Now, just for future work, this is there's so many things we can try later. So there's many tasks we didn't try. So the tasks that would be nice, but we didn't try because just the resources for Spanish were not there, or maybe not very easy to access, was part of speech tagging. Parsing, definitely a syntax-aware task, right? So parsing could benefit, semantic role labeling, and other tasks that are similarly sensitive. More languages, evidently. The problem is, another limitation is that we tried on Roberta, which is completely usable model that is applied in many instances, but this doesn't prove that ChatGPT would have the same kind of gains, right? So as you scale the model up, what might happen is the model has enough of processing power to actually understand that superb can be super bizarre, right? So this is an obvious limitation that probably going a bit further with the model size would help us understand whether this gap remains or whether it can be completely erased by just using a larger model. And then most models used nowadays commercially are multilingual, right? So this is a fascinating task, how to do that if you have multiple languages. If you have multiple languages that are somehow connected, or if you have multiple languages that are not connected at all, can you find a way to apply this kind of setup for multilingual setting? And then, of course, tokenization is great, but tokenization is not mandatory, right? So just to mention, there are methods for doing language modeling both on the level of sentences. These are the concept models, and there are also models that are character level. So they kind of avoid this problem altogether. Okay, this is it. Thank you very much.